All right, so good morning or afternoon to everyone. If you are watching this, it should be on Monday, the 27th. Um, what I'm not here today, so we're going to be talking about units. And then tomorrow on the 28th, on Tuesday, we are going to talk about, we're going to discuss this in class together, really kind of go over this. Um, so, again, I'm doing this kind of live. I don't have a script in front of me. So we're going to see how this goes. Um, so bear with me on that front. Um, Units. I have this joke up here. How much wood could a woodchuck chuck? Right? You think about the answer to that, the common tongue, the tongue twister, and how much wood? If I had two pieces of wood, how much wood is that? So when we talk about units, we're talking about how do we put a number? How do we standardize how much of something we have? So we talked about characteristics like mass and volume when we talk about matter. Right? Mass was how much stuff there is, and volume was how much space it takes up. But how do we actually answer those questions? How much stuff there is? Is there two stuff, three stuff, right? So that's what we use numbers for. We have defined measurements that are standardized so we know how to compare them to other things. So we'll take just an example. I have this at the bottom here. If we have something, oh, that's not what I wanted. If we have something that is 1 meter long, right? So 1 meter long. We know that it is twice as long as something that's 0.5 meters long. We have that scale. By defining what a meter is, we can then use that frame of reference to talk about any other length ever. So that's why we have units, right? If I'm talking about how much something weighs, what the mass of something is, well, here's a scale, a standard, and from that standard, we can base everything else off of it. So let me get back to mouse. So unit systems, right? Here in the United States, we use the imperial or unit system, or we call them American Standard Units at this point. Here is a map of the countries of the world that use the imperial system. They are in red. There are three of them. There's the UK. They actually do it worse in my opinion because they use a weird mixture of stuff. You'll see liters, but also miles. It's We're not worrying about that. Sometimes like Canada will use weird stuff, but the US fully uses the imperial system, right? And we'll talk about what some of these units are that we know about. So things like feet, miles, degrees Fahrenheit, cups, quarts, gallons, all that stuff. Scientists in the US, as well as the rest of the world, use the metric system. Therefore, we are going to be learning the metric system. Some of you have been to other countries or from other countries, have family from other countries. You have probably used the metric system then. You probably have more experience than somebody that's never left the United States. But to make it, fair for everyone, we're still going to go over it. We have here, I have a frame of reference. So when we're talking about units, I will put frames of references. If I say that, okay, the temperature of this water is 30 degrees Celsius, as someone who's lived in America my whole life, that means absolutely nothing to me. I don't have that frame of reference. If you say that the cup of water is 80 degrees Fahrenheit, well, I know that 80 degrees Fahrenheit is pretty warm. So that frame of reference, I will be giving you that when possible to help you understand how cold or hot or how much something weighs um, when necessary. All right. So the basis of units is what is known as the SI units. These are the internationally agreed upon units of the system, and they are all these units, like I said, that standard, what they're based off of, they're based off of some random stuff that probably too much to go into. Like a second is technically the amount of time it takes for some form of radiation to exist, right? We don't need to know that. Here are the 7 base units of the SI system. The 4 at the top that are in red, we're going to go over those. So we're going to go over length, mass, time, temperature. We will get to moles in this class. Not at the moment, but we will get there, right? So moles are how much of a something you have. We're going to get into what that means. How do we convert that? What is the difference between that and mass? We will get there, okay? All right. So first up is length. So length is the measure of distance or how far 2 points are, right? So if I have a point right here and a point right here, they are from 10 to 7. So 10 minus 7, they are 3 inches apart. These 2 points would be 3 inches. So therefore, this length is 3 inches, the distance between those 2 points. Here we have 3 inches. The imperial system, what we use in the United States, we use inches, we use feet, um, 12 inches for 1 foot, yards, 3 feet to 1 yard, and then miles, which is 5,180 feet, I think. I could be wrong on that. I don't like the imperial system, as you can tell, because I don't even know that off the top of my head. Sometimes you'll see in America we use a frame of reference, a football field. There's been news shows where they'll be like, "Oh yes, this is 4 football fields across." It's annoying. The metric system is much simpler. It uses millimeters, centimeters, and meters, and then kilometers. We're going to talk about what all of those different prefixes, the centi, the kilo, um, the the milli, what all that means in a little bit, but it's all based around the meter. That is our unit, is the meter. And just for our reference, 1 inch is about 2.54 centimeters. So we can see here, right, if we have between 3 and 2 right here, it's about 2.5. 2.54 centimeters is about 1 inch. Quick final note about length. Length is going to refer to any distance. So if you were to measure area, you would do, like, what is the area of this square? You would do length times width, right? So L times W. These are technically both lengths. We just use length times width to kind of differentiate between the two of them when we're doing geometry. For our purposes, any length is going to be, L, it will be a distance. So these are both lengths. They both are a measure of distance. It's just in math, it's which direction they're in. All right, just want to make that clear. Here we have mass. Mass is how much stuff there is. So it's different than that mole, which is the amount of stuff. That's a numerical count. Mass is how much stuff there is. We can easily compare it to weight. This is the same picture I used in the very first PowerPoint that I shared with you all, but it is different as we've gonna go here. But we can imagine they're kind of the same. Mass uses the same units that we really use as weight. Technically, weight is talking about newtons. It's about force, but technicalities. For our purposes, mass is the same in everywhere in the universe. The mass of this box is 10 kilograms on Earth, in the moon, or in the middle of space. Um, so mass is just kind of how much matter there is, how much of it. So in the U.S., we use ounces and pounds. So 16 ounces to a pound, and then we'll use tons, which is 2,000 pounds. Not using that here. The rest of the world in the metric system, we use grams, kilograms, and metric tons. Metric tons is 1,000 kilograms. And I'll talk about this nomenclature of the kg. We'll talk about that at the very end because we're going to talk about nomenclature of symbols. So 1 pound is approximately 0.454 kilograms. So there's our units. We'll talk about if something weighs this much, we'll give you a reference. How much would that weigh in pounds? Just to make it easier. So these are the units in red that we're going to be using. Grams is the base. Technically, kilograms are actually the SI unit, but they're, as we're going to see in a few slides, they're related numerically. Okay, time. So time is how long something takes to happen. There's a lot of philosophical discussions you could have of time. You could talk a lot about space-time and Einstein and all of that stuff. We're going to keep time very simple here, right? How long something takes to happen. We know seconds, we know minutes, days, and years, and those are actually the units, the SI units. Um, so for this is the one thing where the U.S. and the rest of the world actually agree on. So seconds, um, right? So there's 60 seconds in a minute, right? And then I missed hours here. And then 60 minutes in an hour, and then 24 hours in a day, right? So we use these. Technically, minutes, hours, and days are not SI units, but they are effectively, they're not officially, but they are used as SI units because they have that direct calculation to do so. So we will be using, if necessary, minutes, hours, and days. Okay, and finally is temperature. So with temperature, we're going to talk a lot about what temperature means at the atomic level. We're going to talk about that next week, right? For now, we hear temperature, we think hot or cold. If it's hot outside, the temperature is higher. If it's cold outside, temperature is lower. Um, this is an introduction. The SI unit of temperature is actually Kelvin. And I miss is Kelvin right here. I miss capitalize this. This should be a lowercase Kelvin, I believe. They are on the same scale as Celsius. Kelvin and Celsius is the same thing, just pushed over by 273.15 degrees. So what I mean by that same scale is if you take a difference of 10 degrees Celsius and a difference of 10 degrees Kelvin, at the definition level, those are the same amounts. The actual value will be different, but the amount of change is the same. That's probably pretty complicated. So just note that for most things we can use Celsius and Kelvin interchangeably. We cannot use Fahrenheit. That's what we use in America for temperatures. Um, we don't use that, but I will give you those conversions for the frame of reference. Because again, if you tell me something is 100 degrees, I know that Fahrenheit, right? 100 degrees Fahrenheit, that's a pretty hot day. 100 degrees Celsius, that is on fire. That's when water boils. But 100 Kelvin is freezing. That's 100 Kelvin is like, let's see, right around here or so, right? It's low. So I thought this was a fun SpongeBob meme. But here you can see the different scales, right? Where does water freeze? Where does water boil? The body temperature, right? So body temperature is almost 100 degrees. It's about here. So we'll be using Celsius. Some instances we might be using Kelvin, but I'll talk to you and we'll explain that and explore that. It's a very easy calculation to get from Celsius to Kelvin. It's just addition and subtraction. All right. All right. So next is prefixes. So prefixes, this is how we change the scale of our units. So if I said that an elephant is 5,400,000 grams, that takes a lot more effort than saying an elephant is 5,400 kilograms. And we can see here that um, the scale, right, they're all multiples of 10. We're going to talk about scientific definition, or scientific notation, excuse me, which is this kind of stuff. We're going to talk about that most likely on either this Tuesday or on Friday. All right. So when we talk about units and converting those units, so we will talk about scientific notation and what all these times 10 to the powers mean. But just note that these prefixes kind of um, they make things a lot simpler rather than just using big numbers. Oh, it's 8,840 billion meters. Just you can change the scale of it. Um, the ones that are in red, milli, centi, and kilo, these are the ones that are most commonly used, and these are the ones that we'll be using the most. That doesn't mean we won't use some of the other ones. We might use nano or micro, um, but if we get to them, we'll use them. And how you use these, you add them to any unit. So take a unit, let's say second, right? I take a second, that's our unit. By adding kilo in front of it as our prefix, that represents 1 times 10 to the 3 seconds, which would be 1,000 seconds. 1,000 seconds is 1 kilosecond. We're going to talk about unit conversions on Friday. This is going to go behind me. I'll fit it in there. So 1,000 seconds is 1 kilosecond. And you can do these conversions. They're all base 10, which is what makes the metric system so easy, is the fact that you can go, it is by multiplying by 10. I just want to point out one other quick point about commas. So just for those, another difference between the United States and other parts of the world is in the United States, we use commas to represent like bigger numbers. So for example, 1,000 would be represented by like this, where we have a comma every 3 units. And then if we were to use a decimal place, right? So let's say it was 1,000 and a half meters. In the United States, we would say 1,000 and we use a dot, a period. So this is 1,000.5, 1,000 and a half, we'll just say meters, right? So this is how we do this in America. Other places of the world, I believe they swap that. So this would look like 1,000. They use a comma. This is how they would say 1,000 and a half. All right, I just want to make that clear. So if you see me doing something that looks like this is equivalent to this. It's just different countries, we write things differently. All right, moving on to derived units. So what a derived unit, we take those 7 base units and we make something new out of it. We combine them to make a new unit. So one example here is volume, right? So volume is, as we said, it was how much space something takes up. We define it in the 3-dimensional field. So we have, length, width, or length, width, and height. So there's 3 dimensions, right? So this dimension, and this dimension. So technically, the SI unit for volume is length times length times length, because these 3 that I've covered in red are lengths. So they are distances, and our SI unit is a meter. So the volume is the SI unit is meters times meters times meters. And if you take a variable and cube it, multiply it by 3 times, that is m to the third, so meters cubed. But we also use in the SI world, and we're going to use this in chemistry, the liter. So the official definition of a liter is 1,000 centimeters cubed. So 1,000 centimeters cubed, which you would get by taking 10 centimeters times 10 centimeters times 10 centimeters. So this is what a 1 liter um, is 1,000 centimeters cubed. We're kind of very often we're going to be using liters because they're based off of it's just another they're based off of the same base 10 system. That's why we can very easily use liters. The United States volume system is this. I hate it. I I I, I absolutely hate it. Um, we don't use it in here. It's even hard to give a frame of reference because there are so many different units. We might know a gallon from like a gallon of milk or a gallon of water, same with like a quart or a pint. But like 1 fluid ounce, like that means like nothing to me. Like I know 12 fluid ounces is a bottle of Coke or a can of Coke, and 20 fluid ounces is a bottle, but that's it. I'm very anti against the United States volume system. Using liters is so much simpler. Um, Commonly, we'll use liters and milliliters, especially. All right, so you can then create derived units using derived units. So we're going, extra on that. So density is an example of a derived unit that uses other derived units. So density is how much mass there is in a space. So how much matter is in a specific amount of space. So this would be how much matter per unit of space. Space is referring to volume. So our um, our formula is going to be mass over volume. So mass over volume. We'll get into what these symbols mean. I'll make sure to make them clear what they represent as we're starting through this, just so that there's no confusion when I just say M over V. What does that represent? This is the same as mass over volume. So this is the two types of units. This line here, this is a division sign. So this is saying you would divide the mass over the volume, right? So if you had 5 grams over 1, let's say, milliliter, your density would be 5 grams per milliliter. And this is going to be our unit right here. We would say grams per milliliter. I actually should, where's the eraser? Keep that a little bit clearer. So the density would be 5 grams per 1 milliliter. That 1 is kind of implicitly said, even though we don't see it. All right. So this would be a density. And we can see density if we take the comparison between a wiffle ball. So this is a wiffle ball, and this is a shot put made out of pure metal. So if they were the same size, we know that the mass of this metal is going to be much greater than the cheap plastic. So the density of this shot put is much, much higher than the wiffle ball. So that's what happens when you take how much mass there is in the same volume. And we'll get into why that happens. It happens a lot with what atoms there are. Different atoms, as we're going to find out, have different masses. There's also the structure of those atoms. We saw they have that neat, solids have that neat orderly pattern. Different solids have different patterns, and that can affect the density. So in this example up here, we can see what happens if the volume stays the same. So this square would represent the space it takes up, our volume. As we add more atoms inside, the density increases. So the more atoms there are in a space, the greater the density because each atom has a mass, right? So the more mass you have in the same space, it increases the density. So this is why we can ask ourselves, what would have a greater density, a gas or a solid, right? This is what a solid might look like. This is what a gas might look like. Depends on how many atoms there are. And finally, so that's all for symbol units. So some common units. I just want to get back to this. We're going to be doing a lab on Wednesday or Thursday, depending on when we meet, where we're going to explore density. How do we solve density? How can we determine what a substance is by its density? As we're going to see, density as a property is the same for a substance. If you take iron and you have an entire block of iron versus a small flake of iron, they will have the same density. Iron has a different density than, say, gold or water has a density. Every different compound or element has its own density. And it doesn't matter how much you have, that density will be the same. We're going to look into that on Wednesday and Thursday. So I'm doing a retake of the last slide. I wanted to add in this slide that I did not have in my original recording. Um, I realize it's probably a good thing to talk about. Um, Units versus properties, just defining what the difference between these things are. Um, the units are the units. That's how we define them. That's what we actually measure with, right? So I'd say, oh, 5 meters. Meters is the units. The quantities is what they are measuring. So a meter is a unit that tells us something's length. A kilogram is something that tells us something's mass. I want to make this kind of clear, the difference between what the unit is and what the quantity is. What are those units telling us about? Because when we go and move forward to the symbols, there's a lot of symbols and nomenclature and all this type of stuff that I really want to get through. So the first thing is that the capitalization matters, whether something is uppercase or lowercase. Uppercase V, this should be an uppercase V, is used to represent volume. A lowercase v is used to represent velocity. Two completely different things. Uppercase M is used for the prefix mega. Lowercase m is used for both mass, the quantity, and mass or meters, the unit. Um, there are some letters that are used for multiple things. It's annoying, and they're not complete all the time consistent. We're going to keep them consistent in this class. There might be folks that use outdated systems that will use something different, but sometimes you just have to deal with it. But it's important to note that m, if you're talking about quantities, you know it's probably mass. So right in this example, this m is a quantity because it's talking about mass. Volume is another quantity. It's what we are measuring. We're measuring something's volume. It's not the unit. So that's why this mass is used in this instance instead of a meter. So you don't add any of the prefixes to the quantities. You will not say, oh, a kilo mass. That doesn't make sense. These prefixes are used for the units. So you would say a kilogram. Going back on that difference between the quantities and the units, right? So you would not say km. You would not use km for kilo mass. You would use km for kilometers. So we're not going to use it there, all right? So there are units and their quantities both have symbols. I'm going to erase and we're going to start again. So the units and the quantities both have symbols, right? So mass is m. and our unit is grams, is G. This is telling us 5 grams is how much stuff we have. So that is its mass, is a unit of measurement. How much of the mass do we have? Well, I have 5 grams. That's how much mass something has. 5G. All right. I hope that makes a little bit more sense. Um, some of the symbols we're going to use are Greek letters. Example, density. This is the Greek letter rho. This is a lowercase Greek letter rho. It is not a P. It's kind of drawing something like that sometimes. It is not equal to a P. It's rho. It actually is an R sound. So this rho is used as the symbol for the quantity of density. So density is going to be seen like this. Some other places will use a capital D, probably because it's easier for young kids learning about density. So I just want to say that you might see that if you're looking up stuff. I'm going to try to keep it to the rho. Okay. When it comes to stuff like this, what does this mean? In the very beginning, I'm going to start by giving you this, something like this. So like if I have a formula, right, rho equals m over v, I will tell you what that means. Eventually, as we get to use these symbols more, you're going to have to memorize what those means. And as you use them, you'll get it. You know, you will get what this m over this v stands for. So the prefixes, which are added to the unit, so not to the quantities, but to the unit. So kilograms is an example of how we would add it to the unit. So the symbol for kilo is a lowercase k. And again, uppercase or lowercase, it does matter. Um, our symbol for a kilogram is kg because this g is the unit for gram and it is lowercase. So kg, like this, is kilograms. Something like this does not exist. There's no Kevin Garnett. Um, this does not work as units because they are uppercase. It makes a difference. Sometimes you will get examples where you have uppercase and lowercase letters. So, milliliters. The milli refers to this lowercase m. So, milli equals lowercase m. And liters is an uppercase L. The reason they do this specifically for liters is because a lowercase l can look like a 1 sometimes, so they don't want that. So, milli is a lowercase m, liters is a capital L, and we get milliliters. Looks like that. We can have something like a megagram. So, if we go scroll back all the way up here, mega is this one, um, right? This is 10 to the 6th, so it's a million. We're going to scroll back down. So, a megagram, mega is a capital M. So notice the difference between the small m and the big M. And then gram, as we said, is a lowercase g. And we get this. Capital M, lowercase g. We're going to, it's funny because this is also magnesium. We're going to talk about symbols for atoms when we talk about the periodic table. So there's going to be a lot of symbols, a lot of this nomenclature that we're going to be using throughout the year, which is why I really explicitly want to go over it now. Another example, a megaliter. Mega is a capital. The liter is a capital. You get two capitals together. Some units, their symbols are more than one letter. So I actually want to go back to another slide. Go back to, we'll go back here. It's actually good. So, for example, a mole is the unit for amount of stuff of a substance. We're going to talk about moles. They're very important. But it is defined by MOL. That is its symbol. They just cut out the E. So a millimole would be represented the M by the lowercase m and the mole by the MOL, and you get a millimole, which you can see here. Other examples that we can see just from this slide is something like years. 8 gigayears, right, is actually uh, erase that. This is a gigayear. It looks weird, but the symbol for year is YR. This one right here, hertz, megahertz, is capital M, capital H, lowercase z, because 1 hertz is like this. You may have heard of megahertz when you talk about radio stations, what their frequencies are. We'll hopefully talk about what that means as well in this class, just as a heads up. All right, so that's units. We're going to talk about this more on Tuesday. We're going to go over this. We're going to be doing a lab on density on Wednesday or Thursday, depending on when you meet. So that's why I really want to go over this so we have this down pat before that lab. All right. So have a wonderful day. I hope you all had a wonderful weekend. I will see you all on Tuesday.